To introduce some context for our research, I have selected a video that shows how demanding piloting can be. In the video, you can see a pilot looking back and forth to his instruments. He is also attentive to what his co-pilot and the air traffic controllers are saying to him, and he replies to them accordingly. That's why tactile feedback has the potential to provide information to pilots without burdening the visual and auditory channels more.
J'exécute et LNAV et niveau 190. Ok. Alors LNAV.
However, flights aren't always comfortable. As much as pilots try to avoid them, aircraft can go through turbulence. Actually, turbulence are more and more likely to happen in the future because of global warming and climate change. Turbulence can have a detrimental effect on piloting. It makes visual information more difficult to comprehend, and it also makes the body to move involuntarily. Therefore, in this research, we want to understand whether turbulence affects vibrotactile feedback perception. And if so, we also want to find ways to design vibrotactile patterns that can be resilient to turbulence. To understand the impact of turbulence on vibrotactile feedback, we started by looking into the most recent contributions in vibrotactile perception. We found some work from Azadi and Jones, which has identified the best parameters to design vibrotactile patterns and optimize their recognition. In their study, they have designed 9 patterns that have frequencies of 50, 100, and 200 Hz, and some duration of 1, 1.5, and 2.5 seconds. They found out that these patterns can be felt and identified successfully on either the finger or the forearm. So we decided to use these similar patterns as a basis for our research. Based on Azadi's findings, we conjectured that if turbulence have an impact on vibrotactile feedback perception, then under turbulence, patterns identification performance will decrease, but high frequency and long patterns will not be affected. The quantity of information conveyed by vibrotactile patterns will decrease as well, and rhythm will be more affected by turbulence than frequency. To understand the impact of turbulence on tactile feedback, we conducted a study where participants had to identify vibrotactile patterns under turbulence. To test our hypothesis, we first designed a set of vibrotactile patterns similar to the ones from Azadi's work. Each pattern is composed of 5 pulses with 4 interpulse intervals. In other words, there are 5 short vibration bursts in all of our patterns. We varied the rhythm and the frequency in our patterns. More details can be found in the paper. So in total, we designed 9 different patterns to identify. Prior research in aviation has explored many locations for delivering tactile feedback. It wasn't clear to us which location would be the most appropriate. So we decided to deliver patterns to 3 different locations which have been studied in the past. First, on the thigh. This location is actually used by pilots in general aviation. They attach tablets to their thigh to look at information such as flight plans, weather forecast, etc. Another location was the wrist. For instance, previous research has looked into delivering weather forecast notifications through smartwatches. And finally, on the end, delivering tactile feedback through the flight stick has already been explored to provide information about the aircraft status. And finally, we investigated different levels of turbulence like on previous work on touch input under turbulence. Turbulence are quite difficult to model, and there is no representative data available. The best we could do was to follow guidance from ISO to reproduce uncomfortable levels of mechanical vibration, like in Cockburn's research. We had 3 levels: a level with no turbulence to provide us with some baseline, a level with uncomfortable mechanical vibrations, and a level with very uncomfortable mechanical vibration. You can find the detailed characterization of the levels in the paper. To summarize, we had 4 independent variables: frequency, rhythm, location, and turbulence. We measured identification success rate and information transfer for each pattern. Information transfer represents how much information in bits that can be perfectly transmitted through our patterns. We had 18 participants, which included 4 licensed pilots, and we collected a total of 4,374 trials across all conditions. The study consisted in identifying some patterns while experiencing turbulence. The study was divided into 3 parts. The first part was a training phase with no turbulence. We wanted the participants to get comfortable with the patterns. During the identification task, the participants were provided with a visual aid that pictured all the patterns. We were not interested in the memorization of the patterns, but their identification. Then, participants had to identify vibrotactile patterns while experiencing turbulence. To allow the participants to select a pattern, we provided only 9 keys that we spread over the keyboard to mitigate any mistype selection that could have happened under turbulence. We counterbalanced the levels of turbulence and the output locations. Finally, upon completion of the identification task, we asked participants to design their ideal pattern. They were invited to change the frequency, the number of pulses, the pulse and the interpulse interval durations. They designed their patterns while experiencing different levels of turbulence. Let's now look at the results. Here is the identification success rate. The x-axis shows the different output locations of the study. The levels of turbulence are coded with different shades of blue, the darkest representing the strongest turbulence condition. The first thing we can notice is that the success rate decreased as the level of turbulence increased for all conditions. We actually found a significant effect of the level of turbulence. Then, if we look at the output locations, delivering tactile feedback on the wrist yielded better performance than any other location. We found a significant effect of location as well. As a matter of fact, based on information transfer, we found that in our study, the participants could at least identify up to 4 different patterns on the wrist and in very uncomfortable turbulence. More details about that can be found in the paper. We also investigated mistakes made by participants. You can see 2 matrices of confusion. The left one shows errors when no turbulence was experienced. The right one shows errors when participants experienced very uncomfortable turbulence. The numeral indices on the top side represent the patterns to be identified. The indices on the left side represent participants' answers. -1 is used when the participant hasn't provided any answer. The diagonal represents all the correct identifications. In the table, you can see the properties of the pattern used in the study. The first thing we can notice is that under strong turbulence, participants didn't always make a selection for the pattern T1, T2, T3, T4, and T5. These are the shortest patterns and the ones that have the lowest frequency in our study. If we now look at the top right corner of the matrices, we can notice that the errors are similar for the patterns T7, T8, and T9. It could mean that turbulence has little effect on patterns with the highest frequency in our study. If we now look within the same frequency, we can notice that the longest patterns were less error-prone. It could mean that turbulence have less effect on patterns that last longer. However, in our study, the rhythm was encoded through pulses with specific durations, which as a result set the duration of our patterns. More research is needed to understand what in our rhythms had an impact on errors. From our findings, we can share these recommendations for designing against turbulence. 1. Disconnect feedback from turbulence. We saw that delivering feedback on the wrist was better than on the hand and on the thigh. That's the only location that was not attached to the structure of our motion platform. 2. Limit the number of patterns. In our study, we found that participants could identify up to 4 tactons under very uncomfortable turbulence. 3. Long and slow patterns work best. 4. High-frequency patterns work best. These were the less error-prone patterns in our study. 5. Provide enough distance between frequencies. We have not discussed this in our presentation, but more details can be found in the paper. To conclude, I would like to propose a protologism, Tactilient. I hope we can do more research to understand what makes vibrotactile feedback tactilient and to support designers creating such patterns.